Good day to everyone, and hello all. This is Ashraf Al-Tahini, the program or the technical program chair for MEOS. I would like to welcome you all to this second live webinar in promotion of the upcoming Middle East oil show known as MEOS, which will be held in Bahrain in November 28th to December 1st this year, with an exciting theme of shaping the future of energy in a dynamic world. I hope we see everyone at MEOS. I encourage you all to visit the conference site for more details, as well as to register for the upcoming events of MEOS. Today we have our speaker, Steve Freeman from Schlumberger, who will be talking about an interesting topic for our industry titled The Role of Disruptive Technology to Survive in a Competitive Industry. Steve is the Global Technology Advisor for Subsurface AI and Innovation for the digital side of Schlumberger. Prior to that, Steve directed the AI developments across the business. Steve was also previously the Vice President of Digital for the software side of Schlumberger. During the last 5 years, he has been involved in the development and implementation of AI solutions across all the domains in the business. Steve currently is part of the AI EAGE committee, and he received his PhD in structural geology from Leeds University in the UK. He has since worked in the energy and minerals businesses around the globe over the last 25 years. Without further ado, the floor is yours, Steve. Please go ahead and share your presentation.
Fantastic. Thanks, Ashraf. Right, let me see if I can share my screen and see if everybody can see it okay. So can you just confirm if you can see the screen?
Yes, we do now.
Yeah, fantastic. Now, thanks very much to MEOS for the opportunity to be able to present today. It's an exciting subject area. What we wanted to talk about today is probably the biggest disruptive element that's happening across our industry today and will carry on happening for the next 20 years. And so that's all around the energy transition. So what we wanted to talk around is within the context of the energy transition, which is going to affect every company in every country in every part of the world. What are the technologies that are out there that potentially can provide a way to maximize the opportunity as we all go through the energy transition. So it is very much a competitive industry, as we all know, and so trying to implement these technologies as quickly as possible to be able to leverage the value is key. So first of all, what I'm going to do is kind of set the overall kind of context in which we all sit, and then look at what are the natures of the technologies that can give us competitive advantages in this space. So overall, on a global scale, then, what we're looking at is an energy transition that is affecting every part of everybody's business, and it will only continue to accelerate. There is fundamentally a dual challenge that we are trying to solve with this energy transition, and that's going to pictured in through here. So, we know around the world anthropogenic emissions are far too high. Fossil fuels account for about 40% of those emissions. Okay, so emissions are far too high for a sustainable planet. And at the same time, the world needs ever greater amounts of energy. So that's the challenge that we face. Emissions too high, but we still need to deliver more energy to allow all parts of the world to continue to develop. There's a dual solution to this dual challenge, and it's around providing ways to dramatically cut emissions from operations. And this is oil and gas operations, but it's also the emissions coming from all industrial sectors around the world, and there's clearly opportunities there. So to cut emissions from existing operations, and at the same time to be able to scale up lower carbon energy production. So if we can implement those solutions, then we can have a global effect going forwards. And when we look at these pieces, when we look at the core areas where the world is going and technology is leading us, it falls into these three buckets. So we have the requirement to be able to reduce emissions from existing oil and gas operations, whether that be onshore or offshore. So technologies aimed at reducing emissions from ongoing operations is critical for all companies in the oil and gas space. The second bucket is around how we can permanently remove emissions from systems, from industrial sources. So whether that be from oil and gas sources, such as gas processing systems, or whether that be the global industrial emissions that come from, chemicals factories and power plants and so forth. So essentially that bucket is carbon capture and storage, and that's a very hot topic in all parts of the world, and it's very much gaining pace in the Middle East as well. And then the third bucket is around low carbon energy production. So these are fundamental sources of energy that have a considerably lower amount of carbon embedded within them. So be that things like blue hydrogen, green hydrogen, whether it be solar, whether it be wind, there's a whole array of different technologies that sit in that space. So those are three areas, and we're seeing kind of activity across all of those. The partners, our companies we work with around the world, all have different blends of those combinations, whichever is appropriate to be able to achieve their big goals. And in every single one of those areas, there is key technologies that provides advantages to be able to implement those and get the value successfully. Just a bit of background for ourselves, just so you can understand some of the context and some of the examples I'm going to talk to. So Schlumberger has been involved in these energy transition projects, for many, many years now. What you're seeing through here is the distribution of projects that we're working on around the world in the emissions reduction, CCS, and the low carbon energy production space. So across all countries around the world, across all regions, there's activity from all parts of the oil and gas industry. And depending on which particular geography, with which regulations, with which requirements, depends on the relative nature of that activity. Okay, but you can see the Middle East is a significant contributor to energy transition projects in that space. So that's the context of which I will, provide some examples around the kind of technologies we see as useful for implementing the energy transition. Okay, so first of all, we're going to go through these three buckets: emissions reduction, CCS, and low carbon energy generation. We're going to start with the emissions reduction side, and this applies equally to offshore operations as it does to onshore operations. Before we get into the technologies involved and where the technologies are today and where they need to go, first of all, we need to understand where those emissions are coming from. Okay, so fundamentally in this space, if we can understand the nature of the challenge, the nature of the problem, it becomes a lot easier to create solutions which are focused at delivering substantial benefits in those areas. So what you're seeing in front of you here is the emissions coming from the oil and gas industry on a global basis. Okay, so it accounts for about 4 gigatons a year, so a considerable amount of emissions coming directly from the operations of oil and gas facilities. This is work that was recently done by kind of McKinsey. What you can see in through here, what we've done is we've broken it down into the core areas where those emissions are coming from. Okay, so you can see that the big chunk in through there, methane accounts for about 60% of all of the emissions that come from oil and gas operations. And that's why there's such a focus around methane. Now, the reason for that is that methane is a very potent greenhouse gas. It's almost 100 times more potent than CO2. So a small methane leak equates to really a very large CO2 leak. So that's why it's such a large part of the emissions challenge. So there's a very big focus from many companies around the world and countries around the world to mitigate those methane emissions. The second big pillar in through there is refinery operations. So refining just simply takes so much energy. It takes something like 5% of the world's energy to do the refining process. And so simply the amount of power that's required to run those systems means that it has a large emissions footprint. The entire extraction, drilling and production part of the value chain only accounts for about 10% of the emissions. Okay, but it's a critical 10% and something that we're all very much focused on. Flaring accounts for about 5% of emissions, crude transportation 5%, and hydrogen production about 3%. Okay, so when we understand where those kind of areas are, then we can look at what technologies are most appropriate for mitigating those emissions. Which levers can we pull that have the biggest impact? And to give you a kind of a sense of scale and a sense of urgency, in many parts of the world, there will be a requirement to be able to deliver net zero operations by 2030. Certainly across Europe and potentially the countries and companies providing products to Europe will need to look very hard about delivering net zero operations by 2030. And that's all parts of the value chain will need to be in that space. Okay, so that's the nature of the challenge on the emissions reduction that we all face. So then it's kind of what technologies can we bring to bear to be able to make a substantial difference in this space. And my background is very much digital and AI, and I'll show you a lot of solutions in that space that can make a difference. So we'll start with the largest one in through there, which is around methane. So methane, is a colorless, odorless gas. If you find a leak, it's actually relatively straightforward to fix a leak. It'll often just be closing a hatch or tightening a screw and so forth. The challenge with methane is about observing where the emissions are coming from. Okay, and the challenge also is that those emissions can come from any scale. So a lot of the emissions come from small little wells in the middle of nowhere rather than the big processing type facilities. Okay, so emissions can come from all parts of the infrastructure, and they can be very significant from any part of the infrastructure. So the challenge then is, how do you observe at the resolution you need across this entire system? And certainly the route that we've gone and some of the other companies are following is around how you have a whole array of different sensors at different scales. So you can have relatively cheap permanent ground-based sensors around individual wells and tanks and so forth. You can have sensors from aerial-based platforms that can give you kind of high resolution data over large areas. And then you can have satellite data continuously monitoring systems that can give you lower resolution, but very good spatial coverage. Okay, so the challenge then is integrating all of that data. And this is where the digital pieces come in. We need to be able to use IoT devices to be able to capture that. We need integration, digital machine learning workflows to be able to integrate that to provide the insights so you can identify where those emissions are coming from rapidly. Okay, so that's solutions that we've developed and deployed in places like South America. It applies onshore. It also applies in the same way offshore. Okay, so that technology is starting to be tested and deployed in offshore environments as well. Okay, so there are solutions to the biggest challenge we face on emissions in the oil and gas space. So that's on the methane side. Now what we'll do is we'll step down through the other categories to look at the other challenges. So refinery heating and power, as I say, it counts for about 20% of total emissions. When we look at these next set of challenges, typically we see responses in two ways. One is around how can we improve the efficiency of the operations we're currently doing to reduce emissions, and the second is how do we potentially completely remove those emissions. So on the efficiency increase side for refinery heating and power, then essentially, the way forward that has been proven to work is around creating digital twins of those refinery operations. Okay, so, and then looking at how do you do heat and power management to be able to lower the overall energy consumption on those kind of facilities. Okay, so we've been doing that with partner groups around the world in places like Japan and so forth, that can make a marked difference in the overall energy consumption on those systems. So digital twins enabling greater efficiency of refining operations is the first step. The second step is around how do you replace the nature of the energy being used to do the processing. So rather than use energy from the grid that probably is being generated with a large proportion of fossil fuels, what you can look at is how do you stand up the renewable energy infrastructure to be able to power these systems. If you do that, you automatically remove all of the emissions associated with the power consumption from those systems. You have a huge impact. So again, this is what we've been looking at. How do you create digital systems to work out the optimum combinations and locations of renewable energy components to combine them together to give you continuous cheap power to be able to power facilities. Okay, so here you've got digital challenges around how do you design and operate these renewable systems. And then you've got digital challenges and opportunities around how do you flex the operation of those refinery systems to be able to deliver you that product you need with essentially no emissions in this particular case. Okay. The next largest component on the emissions challenge that the oil and gas industry faces is around the extraction and drilling. As I say, this counts for about 10% of the emissions in this space. And the answer in this space, as far as we can see, comes through consistently, is if you want to have more efficient operations, not surprisingly, you need to plan for more efficient operations, and you will typically then get delivered those more efficient operations. So, what we've been doing is creating digital systems whereby you can say, okay, well, if I was going to plan a well like this, if I was going to use these types of muds, these kind of casings, these kind of drill bits, this kind of infrastructure, then my emissions is going to be A versus B. So you can make technology choices to be able to design out emissions from things like the drilling and the production process. So that's digital ways in which you can, make better choices, make better plans. There's also technology choices. So say, for instance, if you're dealing with offshore production facilities, if you're in, say, deep water assets, then rather than lifting the fluids to surface and then to the platform and then kind of pushing them to surface, looking at subsea infrastructure, you can fundamentally lower the energy burden of producing those fuels and getting them to market. And that has a dramatic impact on overall energy consumption. But that's how you make things more efficient. The step that we're all going to need to get to is how do we get to net zero operations? Okay. And then, as in the previous case, this is all around ensuring that you can get the renewable energy infrastructure in place and your facilities can respond to that energy system. So how do you design the best continuous low-cost renewable energy supply? And then how can you ensure that you've got fully electrified operations that can respond to the availability of that energy at the time? There's another step in through there as well, just to go a step deeper in the well construction side of the process. It's around digital solutions, but being paired with physical solutions. As I mentioned, by being able to say certain physical technologies give you lower embedded carbon and emissions. So if you're looking at different types of drill bit systems, if you're looking at different types of muds, different types of casings, by taking those different physical systems and combining them together with the digital systems, you can plan for lower emissions wells. And that's what we're doing with partners in various different places in the world. And ultimately, on the extraction and drilling side, what you want to be able to do is not just plan for a lower emissions well, or what you want to be able to do is plan for lower emissions across the entire life of the asset. Okay, so you can look at many different options around how do you optimize the locations of the wells, how do you optimize the production configurations to be able to give you a lower emissions asset through the entirety of production of that system, and integrate that into the continuous reevaluation of the field development plan. So again, that's a place where we're seeing activity in multiple different places around the world. One of the other, very visible aspects of emissions that comes up time and again is around flaring. Okay, so it only accounts for about 5% of the emissions from the oil and gas industry, but it's a very visible 5%. And there are various initiatives like the World Bank zero routine flaring by 2030 that many companies around the world have signed up to. So again, 2 steps in the process. The first is around driving efficiency. So where you have flares today, how do you use digital technologies and physical technologies to make sure they are running at their optimum efficiency? Here's a couple of examples that we've deployed. One's intelligent camera system to continuously monitor the nature of the flare, so you can optimize the performance of the flares from the ground. The other is to use satellite data and continuously monitor flares from space. So there you can ensure those are performing as they're meant to perform. So that's how you can drive greater efficiency where flares exist. Ultimately, though, we all want to be able to design out flares completely from operations, and this talks to creating digital twins of those systems. Okay, so every one of these flare systems is different. There are different fluids involved. There is different infrastructure constraints and so forth. So, and there are many different ways that you can remove flaring from operations. The challenge is, how do you find the most cost-effective way of doing it? And so that's where we've been working with partners to create digital twins of those systems to identify the optimum way of removing flaring from infrastructure. Okay, and the world needs to really accelerate on this to be able to align with the World Bank targets. So that's around technologies for emissions reduction. Now we're going to look at carbon capture and storage. So this has kind of 2 elements to it. One is that for the oil and gas industry, it provides a way to remove emissions permanently from things like gas processing. Okay. But probably more fundamentally, it provides an avenue for new business for people that know how to work with the subsurface and with fluids and transportation. So it's very much seen as a new business area for many companies around the world. So we've been involved in CCS for over 15 years, and we're one of the few companies involved in the full end-to-end workflow, from how do you design the capture and compression, transportation, site characterization, construction, operations, and monitoring. Okay, so from that standpoint, what I'll do is I'll show you some of the technologies required at different places to be able to make this a reality. This just happens to be one of the example operations from North America, and you can see the various different blue trucks in there on one of the wells that was drilled on that facility. Okay, so yeah, as I say, we've been operating across the world in all different jurisdictions and across all different types of challenges. So CCS comes in many flavors. There are onshore operations in places like North America, offshore operations in places like Europe, injecting into depleted oil and gas reservoirs in certain locations. More the favor now is around injecting into saline aquifers. They potentially have larger volumes and less risk of certain challenges. And then you've got the overall objectives of CCS, whether it's around enhanced oil recovery or enhanced gas recovery, or around permanent geological storage. And most of the work these days is very much focused on the geological storage side. And then it's working with a whole variety of different industries, chemical industries, steel, cement industries, and so forth, as well as oil and gas. CCS supports a huge number of different opportunities in this energy transition world. It supports net zero operations for all industries. It supports negative emissions, so bioenergy, carbon capture and storage. It supports blue hydrogen, and we're seeing activity again around the world in many different places in through there, blue hydrogen and blue ammonia, and then gas to wire type projects. The nature of the workflow is kind of shown in through here. You've got an emission site. You have to work out how you capture and compress that. So that requires both physical technologies and digital technologies to be able to optimize that. How you transport it, via pipelines or via shipping. There's a key piece around flow assurance. So these fluids behave somewhat differently from traditional oil and gas fluids. So you need to be careful about how you do all of the flow assurance modeling. It's one of the kind of key risk areas. And then you've got all of the site characterization and optimization piece. How do you do all of that modeling? So at every step of the process, there are digital technologies that allow you to be able to optimize the configuration and principally drive down cost and ensure quality of those operations. Okay, so there's a requirement for digital technologies end to end, and then physical technologies in a few key places around the capture and compression on the surface, and around the well design and monitoring of those systems. You need to take into account technologies when you're looking at the materials that you use. So what kind of cements, what kind of steels you use in the well construction process. When you construct the wells, you have to have different regulatory requirements in through there. And then when you do the measurements, you need to have CO2 tuned capabilities to be able to get the appropriate systems in place. When you put these facilities onto operation, then you need to be able to do continuous monitoring of them to ensure the safe and secure sequestration. So using microseismic data, for instance, to continuously monitor those assets. They are different from oil and gas in that you tend to have very few observation points. So you want to be using optimum systems like fiber optics to be able to get the most information from the relatively sparse points of observation that you have. And then you also need to be able to continuously monitor the position of where the CO2 is in the subsurface. So a variety of different technologies, very similar to what we've always used in oil and gas, but tuned specifically for CCS purposes. And then last, we'll just briefly look at low carbon energy production. So whether this is around geothermal, whether it's around kind of onshore, offshore wind, whether it's around solar, whether it's around hydrogen, again, we've been involved with partners across that particular space, the biggest providers of energy in each of those different domains. So I'll give you a kind of a view of what some of those technologies are. Mostly what we'll do though is focus on hydrogen in this space, given the focus in the Middle East. So hydrogen comes in two varieties that in the low carbon form, that we really kind of care about that much. One is blue hydrogen, which is where we take natural gas and we steam reform it and we capture the CO2 and we put it in the subsurface. Okay, so the challenge there is how do you design and build and operate one of those systems? Technology is really very well established in this space. So if you can create the digital twins of those systems, you can understand how to optimize it. But it is paired with a CCS system. So how do you couple a steam methane reformer and a carbon capture and storage system and optimize across all of it? That's where we can get opportunities in this space. If we flip across to the green hydrogen side, then this is the hydrogen generated by the electrolysis of water. There are key technologies in this space: alkaline, electrolyzers were the kind of older generation technologies. The current generation of technologies are called PEMs. The next generation of technologies, which have much greater efficiencies, are around solid oxide electrolyzers, and that's where our company has recently formed a new company in that space. So the opportunity here is to have dramatically higher efficiencies, and that means dramatically lower costs. Okay, so it is the ability to be able to create hydrogen at massive scale at significantly lower costs. Those are the technology trends that we're seeing across the industry. And the challenge in hydrogen is very much similar to the challenge in oil and gas. It's around, how do you design and build a multi-billion-dollar end-to-end system? How do you understand the flows of energy at every single stage? So for instance, for a green hydrogen system, how do you design the renewable energy components you need? How does it interact with the grid, with energy storage, to the electrolyzer, through to conversion to things like ammonia, through to shipping, through to customer? Right. So what we need are systems, digital systems that can optimize that full end-to-end chain if we want to be successful. And those are the kind of systems that we've been building and delivering with customers. What we've shown so far, though, are individual value chains and individual technologies. This future world, though, is more complex than the one we came from. And if we want to make these things work at scale, we need to think about the interplay between all of these different systems. This is a great diagram that came from the UK Oil and Gas Authority, which kind of highlights the challenge, right? So you've got emissions coming from facilities onshore, so CO2, that then gets sequestered in the subsurface. You've got natural gas that's being produced and potentially being delivered as electricity with gas to wire. It's potentially being converted to blue hydrogen. Also, you've got renewable energy components that are being used with an electrolyzer to create hydrogen. So you've got the continuous flow of all of these energy systems feeding into each other. And where the most successful people will come is when they're able to integrate all those pieces together. So, this for us is the next big major challenge: multi-sector optimization. Okay, and this is what we've been working on with a variety of different groups. So here is a notional place, just happens to be near a coast. This particular case, we've got offshore wind generating power. That offshore wind is either delivering power directly to customers, or it's being used in an electrolyzer to create hydrogen. When there's excess hydrogen, that's then being stored in the subsurface. So that's the digital model of that system, and it's a physical location in the world, where that data comes from. But then you've got CO2 that's coming from different facilities that needs to be sequestered in the subsurface. You've also got methane that's being produced, natural gas that's being produced, that's either being delivered as natural gas or can be converted to electricity and delivered to the customer. You can also have biofuels in the system, but ultimately what we want to do is optimize across all of those pieces together. Okay, so you've got optimization across all of those demand and energy production components, making sure you can deliver the lowest cost, most sustainable system for a particular region. So, that's the nature of the challenge we see ahead of us, and the technologies required to be able to deliver on that. There are these three kind of key areas around emissions reduction, CCS, low carbon energy. There are digital technologies that are fit for purpose today to attack these problems. But fundamentally, it's all around, for a company or for a country, there is a specific net present value that needs to be delivered. Okay, the biggest scale targets for the company, that typically has oil and gas targets associated with. Now it has emissions targets that go with that. And all of those components that we've just talked about are there purely to deliver that central theme. So the gas production, oil production, CCS, renewable power, blue and green hydrogen, and emissions reduction technologies are there to deliver the most value while meeting those particular targets. And that's the challenge we see around the world, and we see with customers in all parts of the world. So hopefully that gives you a flavor of our view of where we see some of the big technology challenges, the big disruptions that are happening in our industry. And we expect this area to really accelerate in all parts of the world. So with that, I thank you very much for the opportunity to present and for your attention, and I will gladly open up for questions. So there's a question in the chat. If anybody does have any questions, then please type them for us to see. So there was a question whether any of the materials will be shared from this presentation. Then yes, we'll consolidate the materials and we'll provide a suite of those that can be shared. So thank you very much for that question. If anyone wants to fire in any other questions, then please do. Okay, very good. Okay, so thank you for the comment there. So excellent presentation. Can you elaborate on how we can monitor CCS using microseismics? Yep, absolutely. Okay, so the challenge on CCS is that if, for instance, so we typically inject it as a dense phase fluid, and if you're injecting it into a relatively virgin pressure reservoir, you increase the pressure inside the reservoir. So this is injecting it into saline aquifer systems. Okay, so as you inject that dense phase fluid, you're raising the pressure of the reservoir, and that can induce microseismicity. So the microseismics is used to be able to calibrate, what's that safe injection limit that you're operating within. So if you want to directly image higher concentrations of CO2 in the subsurface, then seismics is a very effective mechanism at doing that. You need relatively well designed but relatively low resolution seismics to image CO2 in the subsurface directly. The microseismics is much more around ensuring that you're not inducing microseismicity that might potentially cause a breach of the top seal. So thank you very much for that question. Excellent. Right, just going through some more questions through here. Okay, welcoming and transparent. How welcoming and transparent are E&P firms when it comes to opening up around scopes and challenges? So yeah, really quite open. I think everybody recognizes this is a place where we all have to kind of come together and find solutions. Nobody has solutions to all of these challenges. We're all learning, and it's very much a kind of an open partnership. So we've seen really quite a large degree of openness in this space where everyone's saying, okay, well, how can we work together in a deeper, true partnership to fundamentally solve this problem? Because if we can't solve it, it's going to be at the detriment to all of us. So yeah, it's been really a very positive experience in this space. Okay, next question. Mike, can you share any specific drilling rig optimization examples? Yeah, okay. So what we have been able to do is we've got a significant kind of history of kind of operations in certain areas, so we can look at what the plans were that went into designing particular well construction jobs. So we're doing this in kind of like our drill plan technology, and then we can continuously observe what was the nature of how successful that well was when it was constructed, using our drill ops technologies. So we've now drilled many thousands of wells with those digital records, and that then allows us to be able to say, actually, this bit with these kind of configurations has been able to deliver significant benefits. So when we've looked at that, we've seen kind of benefits of 15-20+% around non-productive time, around kind of bit trips and so forth. So yeah, there's if you contact me separately, I'll be very happy to present, share you some more materials in that space. We presented some of that in the Middle East Drilling Technology Conference just the other day. Question: satellite monitoring will be through hiring satellite or personal satellite? Well, there's a combination. So if you look at, say, some of the observations of flares from satellite data, then we've been working with and processing publicly available data. There's also companies like GHGSat, for instance. If you're looking at very high resolution imaging of methane from space. Okay, so it's a combination. For instance, if you're looking at the methane problem, there's public domain data from a range of different satellite providers that is really very coarse. And then you've got private suppliers that give you kind of higher resolution data. If you are thinking about the methane problem in particular on that comment, then satellite alone doesn't give you enough resolution. You need to combine it with ground-based data and aerial-based data to be able to kind of get the resolutions you need to really make a difference in that space. But great question. Thanks for that. Okay, for example, an operator in Oman has a platform where it enlists challenges and invites disruptive technology firms to review presentations. Okay. So the question here then was, are there places where there are essentially kind of shoot-offs, by the sounds of it, where an operator has a particular challenge and then says, can different groups come in to demonstrate how those will be successful? So certainly those kind of technology shoot-offs are pretty common. I think more what we've seen in the energy transition and emission space. So we've done a lot of those in the AI space, which is where I was very much focused the last kind of 3 years. In the emissions reduction space, I think we've seen a greater degree of openness. So instead of an operator saying different technology providers come in and see how well you can do at imaging things, we've seen more of a partnership type approach where it's been, okay, we've got a facility here we want to test. Let's actually do this together to understand what would be the optimum combinations of technologies, physical and digital technologies, to address those particular challenges. So that's the kind of nature we've seen in this kind of emission space, which is, I think, very healthy, because driving down emissions is for the benefit of all of us in this space. Another question: do you see a trend of certain technologies being applied specifically to certain regions compared to others? Yeah, absolutely. So carbon capture and storage, the vast majority of that is still in the US. That's where most of our operations are. It's where most of the world's CCS is being conducted to date, and that's been principally driven by the regulations. So there were very clear, well-established regulations in place, which meant people could do the investment to be able to create those businesses. In terms of other technologies, so if you're looking at emissions reduction, then, for instance, Europe is very strong on that. Net zero will be the default for all operations in Europe by 2030. There's relatively little doubt in that space. And then if you look at low carbon technologies, offshore wind, very, very strong in the North Sea, growing in Korea and China, and starting to grow in offshore US. And we're working with a number of the very big offshore wind providers in that space. So as with oil and gas, it's driven by where the demand is, where the markets are, and how you can connect them together. Another question: do you think 3D printing and digital warehousing could fit into this line of work? I think there's less of a direct analogy at this point. I think on some of the manufacturing components and optimizing kind of pieces around manufacturing, that's where I think the real kind of sweet spot for the 3D printing components is. But thanks for the question on that. Another question in through here: existing producing oil and gas wells, about 20 years old. How can they implement digital twin technologies? Yeah, very good question. So certainly digital twin technologies do not require a wholesale set of new equipment. The vast majority of them are retrofitting low cost sensors onto onto physical systems. So we've done this in a number of places, say some examples over in the Far East, where there are a whole bunch of analog gauges on some production systems. Simply put a low cost camera and an intelligent IoT device, our Agora device, on it, and we could then digitally kind of monitor and optimize those systems. So wherever you've got existing mature infrastructure, there are relatively straightforward ways of digitalizing that up so you can kind of optimize those operations. Yep. Another comment through here. Thanks for an excellent presentation. Well, thank you very much for that. What are the critical design criteria for CCS wells? Okay, so CCS wells, you need to, in terms of the economics, you need to be able to make sure you've got the maximum amount of injectivity on that reservoir. So you need to have high porosities, high permeabilities, and the right kind of completions in place for that. The other key piece is when you inject CO2, it becomes a relatively aggressive fluid in the subsurface. So you need to ensure you have the right cements and the right steels to ensure that you don't get corrosion on those systems. Okay, so that's a requirement. Fundamentally, if you look at the legislation, so for instance, in the US, there's a Class 6 type of well permit required, which is higher than any oil and gas permit for CCS systems, and that's fundamentally around how do you ensure that these CCS systems don't potentially interfere with kind of human aquifer regions. But happy to go into any level of detail on that at some other point. Thanks for the presentation. I want to ask if you're aware of any countries' projects where all components are integrating production, energy consumption, CCS, and being optimized. It's an evolving space. So certainly, the blue hydrogen is relatively straightforward because that's where we're getting SMRs. They have to be coupled with CCS facilities. So we're seeing that with some operations that we're involved in North America. That's certainly coming across into Europe now and other places. Where we're looking at kind of integrated energy systems, there is opportunity, I think, in this space. What we have yet to get to is a place where we're seeing the real value being delivered by integrating renewable energy into oil and gas operations, into blue and green hydrogen systems. So we're starting to have conversations with more kind of government level organizations, bigger than individual companies, because that's where the real value of this kind of multi-segment optimization is occurring. So a variety of conversations in different parts of the world, from individual islands through to kind of large nation states in that space. How do you see renewable energy capability roll into electric actuation? So one of the if you look at the amount of emissions that come from production operations, there's a significant component coming from the amount of energy that is simply used to run the operations. So whether you're looking at kind of subsurface pumps and so forth, or whether you're looking at the refinery operations, etc. Renewable energy instantly provides a way that you can net off any emissions associated with the supply of power to that system. Now, obviously, what you do need to do with those systems, ensure that you've got continuous energy or robust delivery of that energy for those kind of systems. But that's simply a design problem. It's not a fundamental challenge with renewable energy. You need to look at battery storage. You need to look at potentially having kind of hydrogen backup systems to be able to do that. Another question. Thanks for the presentation. You mentioned integration is essential part of digital transformation. How do you define integration here? Is it database integration? Is it using the same tools to solve different problems? Is it using different input types, etc.? Yeah, great question. So integration is always the challenge in our industry. Whenever we have seen groups be able to integrate across borders, then they've typically seen benefits. So whether that is integration between the geologist and the geophysicist, if we go back kind of 10, 15 years, now it's more about the integration between subsurface and well construction. But the more the integration that we see in the energy transition space is the integration of different technologies. So for instance, if you want to reduce the emissions from your company, then you need to look at, okay, what are the different levers can be pulled? Okay, we can stand up blue and green hydrogen to produce low emission hydrogen that can be used in our gas processing facilities. You can look at standing up renewable energy to be able to offset the emissions that come from the electrical use across your production and refining operations. You can look at standing up CCS systems to be able to reduce the emissions that come from your gas processing facilities and help enable greater gas and oil production. So it's that more circular thinking that I was really referring to in this space. It is a challenge. We don't naturally do it, but there are great benefits to be had. So yeah, we said I'll share a copy of the presentation. Is there a huge advance in the extraction technology of solar energy coming in the next 10 years? Will the world be less dependent on fossil fuel energy? Okay, great question. So solar PV is, what was it, the latest auction in that was in Saudi delivered the lowest ever cost of auctioned energy. So this was at 1 cent a kilowatt hour. So that, to put that in context, the price of that PV solar energy that was going to be delivered in Saudi was about a fifth of what it would cost to get that energy from a combined cycle gas turbine plant. Okay, so solar PV and wind are now demonstrably the cheapest forms of energy if you want electrical power. The challenge, though, is you need to have that power on a more continuous basis, and this is where we're looking at, how does battery storage linked in with pumped hydro, linked in with hydrogen, potentially from natural gas, allow you to have a continuous energy system. Okay, question from Will Bradbury, an old colleague from mine. What do you see as the ways to drive multi-sector optimization out of integrated roles for governments and regulators? Yeah, interesting. So I think there will naturally be a drive from companies to be able to drive their own internal optimization. What I think is certainly coming down the track really quickly is that governments need to be able to demonstrate reduced emissions and a more integrated kind of circular economy to the world. So to align with Paris, to align with kind of the kind of COP 26, etc. So I think what we're expecting to see, and particularly from NOCs inside larger nation states, is the requirement to be able to look at how does a country overall be able to deliver the energy it needs, the value it needs, and the emissions that it needs to comply by. So we're having conversations with various different groups in that place around how can you integrate and optimize across an entire nation to ensure that you've got the CCS, you've got the hydrogen, you've got the oil, the gas, that can all come together to deliver what the nation needs to deliver. And last question in through here, what would your advice be to young professionals or hardcore upstream drilling production engineers where to focus on overlapping technologies? For example, high enthalpy geothermal projects, CCS, CO2 transmission lines, titanium risers, okay. Right, okay. Thermal, interesting. Ultimately, it has a scale and a cost challenge to it. So in the right geographies and the right locations, geothermal is very effective and great. But ultimately, you won't be able to do that in all places. Okay, so onshore wind, offshore wind, and solar will win in most areas in those spaces. CCS is clearly here to stay and currently has a CAGR of about 45%. So CCS very clearly required to be able to decarbonize many of the hard to decarbonize industries. Hydrogen, the hydrogen economy looks to be playing dramatic growth across Europe, North America, China, Japan, Korea, and that's then being delivered by the places that can produce low-cost hydrogen, and that are places like the Middle East and North Africa. So I would say hydrogen, CCS, offshore wind are places where there's a lot of alignment with the capabilities and technologies that you're probably very used to. So thank you very much for all those questions. That was fantastic. And I really appreciate the opportunity to present. Ashraf, do you want to say anything, or should I close? Okay, sounds like I should probably close. So I'll just reiterate, yeah, a huge thanks for everybody for attending. Thank you very much for MEOS for the opportunity to let me present. It's been great, and I really look forward and hope that we can work together to be able to make this energy transition a reality. So thank you very much, and I hope you have a great rest of your day.